Hey guys, Dr. Calkins, week 15, chapter 12, solutions. Only 2 chapters left, both of which include math. This one does have quite a bit of concepts to cover. We'll cover that first. We'll come back in a second video for the math a little bit later, although we might introduce some here. Title of this chapter though is solutions. So remember that means homogeneous from chapter 1. Homogeneous mixture. So in order to have a solution, you have parts of the solution. So one we call the solute. That's the little guy. That's the minor component. So typically that's things like salt or sugar. And then when you put salt or sugar into a solution, it's always dissolved in, or diluted or whichever, in the solvent. And that's the major component. So a good example is water. Water is almost always our solvent in Intro Chem anyways. So if we have these pieces, what we want is to add them together, because then we get the solution. And that's the mixture when stirred together, looks the same. So what's important about these ideas though is this is the minor component, major component. These are pieces. So piece, add them together, you get the whole. That's a percentage. And percentages were a major part of our last homework. They're going to be a small part of this homework as well, but definitely the easiest part. So we'll cover percentages in the other mini lecture for this chapter with the other math problems. But know that that's a big issue. If they give you salt and water, you're going to have to add them up. So oftentimes if they give you salt and water, it's going to be the solute divided by the solute plus the solvent times 100. That'll give you a percentage. Keep in mind, this is just a solution, so if they give you solute and solution, you can just divide and times it by 100 and you're done. And that's the last several matching questions of your homework. So just pay attention. If they give you water, water's part of the denominator. You have to put the solute, which is also on top. So the biggest mistake students make is they put the little number divided by the big number, but if that big number is water, don't forget to add the little number. If that big number is the solution as a whole, then you're fine. So be mindful of that. When you make a solution, there's 3 stages. So very similar to those ideas above. The first one is the solute has to separate. So that's step 1. When the solute separates, it requires energy. If you think of salt, when you put it onto, say, ice, it gets very cold. So if you have this little cubic structure of salt, you're going to have to take energy to pull those Na plus and Cl negative ions from it. You need the help of something like water. Water is very polar. These hydrogens are partially positive based on the other chapters we've covered. Oxygen's very electronegative, so it feels negative. These hydrogens are like tweezers. They're going to pinch onto those chlorines and pull them away. That takes energy. So the solution gets colder. Oxygen's very electronegative, so it's going to find positive atoms and just like a little harpoon, stab at those sodium plus ions, those cations, and pull them away. That too requires energy because you're pulling it from a cavity of negative chlorides, which are attracted. So all of this requires energy, so all of this is how we make homemade ice cream. When you put water and salt together, immediately they have to break each other apart, and that requires energy, so it gets cold, hence cold enough to freeze milk into ice cream. Ironic that we put salt onto ice in the winter. It actually gets very cold first before it ever can get warm enough to melt the ice. We'll talk about that coming up. Step 2 is the solvent has to separate. So when the solvent separates, that also requires energy. So what this means for both of these steps is we're getting colder. When the solvent separates, it's now hydrogen bonding that has to break. So we have these water molecules from our previous chapter. We know that they have an attraction to each other. This is called hydrogen bonding. These have to break, just like these little Na to Cl attractions had to break in that salt crystal lattice. These hydrogen bondings have to break to make room for the new sodium and the new chloride ions that are floating around. And that takes energy. So we get colder. So the first two steps get colder, regardless of anything that happens. If you remember from our second experiment, putting baking soda into water got colder, so we had to warm it up to melt our ice cubes, and this is why. So these first two steps actually make salt on the highways in the wintertime cold. So how do they ever melt the ice? Well, in that third step, and the most important step, here we get into solvation. Different from salvation. Solvation is when we make now a solution, and this releases energy. So in this case, we're going to get hotter. So there's a trade-off. How much energy is required in the first two steps to the last step? If the first two steps require more energy than is ever released, it stays cold. And this is how they make cold packs in those first aid kits. The little pellet that's inside that you snap, it requires energy to break apart the solute that was inside. It takes energy to make room for the new solution. And it never gets enough energy back, so it stays cold enough to ice down a swollen ankle. The opposite's also true. If what's inside that pellet when it snaps requires energy as the solute breaks apart from the pellet, as the solvent separates that's around the pellet. And now we get this new attraction between solvent and solute that produces so much more energy. Now it gets super hot. Now you have a hot pack instead of a cold pack, and maybe keep your hands warm in a beer stand or who knows what. So that's the major difference between how solutions are made. It's a trade-off on the first two steps, and then this last step, which requires energy is the first two, the last one releases energy. So a lot of things may have kind of overall the same, so it stays room temperature. So it might feel cold as you stir, but as you stir, the energy released makes up for it, so it stays room temperature, and that's oftentimes the case. But there are three steps, and in this solvation step, what happens is something called hydration. We actually did a hydrate lab that used this idea, but as water now gets new attractions, for example, to a sodium ion, or which is electronegative, or these positive hydrogens get an attraction to a chloride ion, this new ion dipole attraction, that's new energy, that's heat released, and if that's more than, at least originally, in those first two steps, we overall get hot. If the attractions made here and here aren't very strong, and they're definitely not stronger than the ones we broke on our way to get there, then it stays cold, sometimes very cold. And that's the major difference between hot packs and cold packs. The last thing we need to understand about solutions is something that we just kind of mentioned up here a moment ago. Like dissolves like. So water dissolves salt. So uniquely when this happens, water is polar, and it dissolves very ionic and very polar salt. So if you're polar, you're going to dissolve other things that are polar. So if you're water soluble, we had all kinds of solubility tables to help us with that. It was really this after this idea that if you're ionic, you're polar, water's going to like you because water can attract you. This is also why things like oil dissolves gasoline. So when you mix gas for a two-cycle kind of engine, oil and gasoline mix very well. And that's because oil is non-polar, so it's going to dissolve and make a solution very nicely into gasoline, which is also a non-polar hydrocarbon. But this also tells us that water will not dissolve in oil. And that's because water is polar, and it will not dissolve in non-polar oil. So we saw these ideas a long time ago, we just didn't call it what it really was, and that was solubility, or in this case, making a solution. There are some molecules that are a happy medium in between, so things like soap. Soap has that long hydrocarbon tail. So this hydrocarbon tail is nonpolar. Eventually you get that carboxylate salt from a fatty acid. Saw that in our biochemistry chapter. Here we are ionic, which is very polar. So here we have the best of both worlds. We have ionic and polar that loves water. And we have this hydrocarbon tail that loves oil. Problem is, it makes a micelle where all those little tails grow together in the middle, so you have to give soap some pressure, now more than ever, to keep your hands clean of anything like coronavirus or whatever it is. So because of like dissolves like, those tails like each other enough that they encapsulate themselves. The outside is polar, so you have to press down on those little soap molecules in order to get them open. We talked about that earlier. And before we switch to our math problem, one thing to think about, this comes from the Wizard of Oz. The Wicked Witch of the West, they threw water onto the Wicked Witch. So when you throw water onto anything, you don't melt. Melting requires heat. If you're going to do anything to that Wicked Witch, it's going to be to dissolve. So Wizard of Oz is not very scientific, because water dissolves things, water doesn't melt things. But that's a movie. We'll come back next time.